This is online lecture 3, Scale and Generalization. It's going to relate to, I believe, chapter 6 in the textbook. But once again, our purpose here is to continue to build your GeoGeek vocabulary. Also, very quietly, we are further emphasizing the subjective role of you, the cartographer. We make decisions, good or bad, about what to show and how to show it. I will begin by talking about scale and then follow by focusing in on generalization. That said, these two do go hand in hand, thus they're pairing here. We have to think about scale no matter what, no matter the reason, when making maps. At least until we get to the point where we have a 1-to-1 ratio with virtual maps where we're looking at them and all this far out stuff. We're not there yet. And so what we have to do is we have to, once again, generalize as we take this round Earth and put it inside a computer screen or on a piece of paper. And many of us already use and apply scale. Whenever you zoom in and zoom out on a map or a picture, you're changing the scale. Even further, microbiologists have to think about how things are obviously at a microscopic scale as they observe super teeny tiny little things, whereas planetary scientists think of things on an immense, out of this world scale, whether it be across space or time. That means, once again, we have to make decisions. For example, at what level zoom does my map look good? In digital computer cartography, the representative fraction is the most common way we show or display scale to the map viewer. Personally, back when I was in college, during the end of the pen and ink days of cartography, we really never talked about RF scales. Instead, because we were working with paper maps back in the day, graphic scale and occasionally written scale were the ones that we used because we're making a fixed graphic scale or a fixed written scale for a paper map. You can't zoom in, zoom out to a paper map. Aha, but now we can zoom in and zoom out. And so that's really changed how cartographers view scale. Even better today in computer cartography, the RF scale, it's pretty much done for us. We don't really have to worry about it. We don't have to figure it out. We don't have to do all the things we used to have to do back in the old days. And once again, RF is expressed as a ratio where you have 1 on the left side of a colon and then another number on the right side of the colon. All this is doing is informing the map viewer of the relations between the map, the left side of the colon, and Earth distances, the right side of a colon. So when you see an RF, you want to interpret it like the following. Let's say we have an RF of 1 to 25,000. What that means is for every 1 unit of measurement on the map, that is equal to 25,000 of those same units in reality on Earth. In other words, 1 centimeter on the map equals 25,000 centimeters in the real world. Or 1 inch on the map equals 25,000 inches on Earth, and so on. So once again, building the vocabulary. Here's two often confused terms, small scale and large scale. And it makes sense why they're confused. You'd think, wait a minute, 50,000 is larger than 25,000. Why is it smaller? Just gotta have to think about it differently. What this is once again a ratio. So instead of putting the colon there, put a divide by sign. And so think of it as 1 divided by 50,000. And then this is 1 divided by 25,000. Which one of those is a larger number now? The result is this would actually be a larger number. 1 divided by 25,000 is larger than the result of 1 divided by 50,000. Or just make it simple, we have a ratio of 1/2 or 1 to 2 and a ratio of 1 to 4. The 1/2 is 0.5, the 1 over 4 is 0.25. 0.5 is greater than 0.25. So we refer to small scale as a more zoomed out perspective that covers a larger area but has less detail. Whereas a large scale map is one that's going to be zoomed in quite closely and it's going to cover a smaller area and have more detail. And as I noted, ArcGIS stores this for us. And so here we see on the bottom left of our map, this is the same one from earlier in which we have a 1 to 252 million, which we're way zoomed out. And so we would call this a small scale map. And eventually we zoom in and get to a larger scale. And so in the 3 maps that we're going to look at, this is to be the medium scale, in which now we have a representative fraction of 1 to 27 million. And then eventually we zoom into the area that we want to look at, in this case, Marion County, in which it's now at a very large scale compared to our first map, our small scale map, in which here we have a 1 to 488,000 ratio. So we use another term called display scale here that says, okay, we have the scale that we want to view whatever we're trying to view. So here, beforehand, I said I want to make a map of Marion County and the surrounding counties. I would want to choose this as my display scale. I would not want to choose this or this. So it's very important. You're going to see the word display scale. What that means is your desired scale, the desired level of zoom for whatever you're trying to do. Once again, if we're looking at world data, this would be a great scale. Whereas if we're looking at county data, in particular central Indiana, we'd want to zoom in to a much larger scaled map and, of course, center it on our focus area, Marion County. And, of course, there's kind of a formula for some of this. And so here we see a relationship between scale and info. What can be depicted on a 5 by 7 inch static map? And so essentially, what would be the proper scale to show whatever we're trying to show? And so if we're trying to show the entire world, we'd of course want to have a scale, in this case, that's above 1 billion. If we want to show a scale that shows a large metro area, like all of metropolitan Indianapolis, we'd want to find something more around 1 to 1 million. And of course, if we're going to show our house and its detail, to show the edges of the house, to show the property lines, to show where a swing set might be, all of those things we'd want to zoom in and have a much larger scale, a 1 to 100 scale. What I mean here with this general rule, don't exceed 10 times change in scale, this is from the textbook, and what they say is essentially what you want to do is if you are wanting to show a house and you're wanting to show the house its precise location, if you want to show the footprint of the entire building or an entire house, the entire structure, and it's all of its detail, its little nooks and crannies, then you'd want to zoom in, but you would never want to have that particular level of detail when you're showing something at the urban neighborhood or the small city. You might be able to pull it off doing this the city block to have that level of detail to show your house. However, if what's going to happen is if you zoom out to these larger areas and smaller scales, essentially what's going to happen is the house is going to be lost. It's really not worthwhile to still show it. Essentially, it's not going to be able to be depicted when we're zooming out that far, is what I'm trying to get at. And so you do typically want to keep it next to each other. And so if you're going to show the detail of a house, it's going to be able to pull off there in the city block. But once you zoom out any farther, it's too far. It's exceeded that 10 times change in scale. Scale is also tied to something what we see here called data resolution. And you're also going to hear the words precision. So is your data precise? What's the level of precision with it? Or its granularity. Is it coarsely grained? Or is it extremely high detailed granularity? And so those are other synonyms, other terms that you might hear here in GeoGeek language. Data resolution, we have two different ways to think about this. And we think about it in terms of raster data. And I'm not going to go into this. This is something covered in GIS, but there's different ways that we show geographic information. And one of them is called a raster. Essentially, just think of it as a photographic image. And it can be an aerial photograph or satellite imagery. And here, when they use the term resolution, they refer to the width of a pixel on your screen and how that relates to actually Earth's surface. And so we see high resolution, extremely detailed imagery, being ones that were maybe what we would say 1 meter. Whereas a lower resolution, in this case, comparing these two numbers, would be a 30-meter image. And so what that says is this particular pixel covers 30 meters in reality, whereas in the first example, the higher resolution, that one pixel shows 1 meter of distance across our surface, and so obviously a higher resolution. We also think of in terms of vector data, and that's going to be the focus of the rest of this pretty much video, is using vector features, focusing on vector features, things like census tracts, block groups, states, dots and lines and polygons added to a map. And we think about data resolution, higher resolution are going to be those super small units like the block group, the neighborhood group, tracts, whereas lower resolution would be things like studying things like the states, countries, in which so we kind of zoom out in terms of the data that we're using or trying to depict. So the moral of the story here with these two is as you zoom out, the resolution goes down. And this makes sense. And so this is why there's a need for scale at many different levels. And so once again, this is, 20 years ago, we really weren't too concerned about this because we were like pushing at all these maps in which people can zoom in, zoom out, and all of that. And so we had to think about scale in terms of multiple scales: large scale, medium scale, small scale. Further, we also need to think about scale and how it relates to resolution. For example, if I have an image of the entire world, I'm going to use a lower resolution. But as I zoom in, I want to see a higher resolution because I want to see the detail of the features around my neighborhood, around my city, around my village. Whereas when I zoom out, I really can't see those. I'm not concerned with that. And so the level of detail or the resolution is of less concern as I scale out. For example, here's an image of Indianapolis, and it's cool. This is useful. I don't need a higher resolution than what I have here. The level of detail is about as good as it can be. I can't see individual houses from this high or from this small of a scale, but I can still see, where the river is, downtown, Speedway. What this is a satellite map from 1985. But when I zoom in, I can see the resolution. It's not that good. Whereas today, we have much higher resolution as we're putting out imagery in which the detail is extremely good, in which we're now working with 1 meter resolution. Just imagine the resolution that a UAV or a drone could do that's even better using the same tools that these satellites way up in the sky or airplanes flying way high are essentially capturing here. Drones or UAVs can capture at a much finer detail, at super high resolution, and finer granularity than ever beforehand. Let's take some time, have some deep thoughts. Why do we generalize things? This is beyond map making. Why do we generalize things in life? It's maybe more efficient to do so. I don't have to really go through the details. I can make generalizations. I can kind of make a more broad statement because I just don't want to get too specific. I keep things simple. But I make the caveat, of course, that it's not exhaustive. I'm not covering every detail, but I'm pretty much covering most things. So that's why I'm making a generalization. So it makes me think of the map earlier I showed this semester of the subway map there in London. It was kind of the whole idea was they redid the subway map, didn't really care about where everything was located. They instead they generalized the location of things, and it made it more visually more appealing map because they used generalization. They generalized the map instead of making it super detailed, super specific, and having every single thing on the map. Just focus on the things people need. And we also like to generalize things, especially when we start doing statistics and math. It makes things a little bit easier to do our calculations, especially in our spatial databases. Just pretty much in humans, we just like to put things in containers. We like to summarize things, and generalizations is kind of an example of a summary. Which we're making summaries of a particular group or particular population or a particular phenomenon. So as we go up and down in scale, it's going to require us to make generalizations. And generalizations, key to them is we're going to have a reduction in the complexity and the detail, so we're going to lose out on that. But the idea here is that's okay because we're not losing the main purpose of the map, the information that's being created from whatever we're creating. And so the key idea here is we want to use data that is the correct level of detail for our map scale and, of course, for our purpose. There's two ways to think about this, and we have selection and symbolization. So for selection, think of this as kind of which features do I include at a certain scale. For example, do I keep all of the cities and towns in central Indiana or just those above 20,000 people? So I'm trying to make a choice there. Do I have them all? And if I do have them all, there might be a problem. I might have too many names, too many dots on the map if I have every single town, because there's a lot of towns in central Indiana. How about if I just choose those that are above 20,000? Essentially what I'm doing is I'm making generalizations. I'm essentially changing my map, making a decision, and selecting just those that meet a certain criteria. Symbolization. How do I alter a features design based on the scale? Do I use the polygon areas of each of these cities that are... Now for symbolization, okay, so for these cities that I have, these 20,000 above cities, do I show the areas of each of them, or did it just simply show each of them as a dot? Essentially, I'm trying to make a decision there about the symbol that I'm using. Am I using a polygon for each of these cities and towns that are above 20,000, or am I using a dot? Which one looks better? Which one am I going to see all of them more clearly when I'm at a proper scale? As you can see, once again, this is subjective, and it requires us to have deep thoughts, requires our attention, and we have to ask, does accuracy matter? Does the precision of my map matter? What am I analyzing? And I got several examples here. And so when we see also is, thinking in mind, the key here is we're trying to maintain accuracy. We want to show things properly, but not always do we want to do that. And so as it says here, our overarching goal still is to maintain the spatial accuracy of things, for the most part, as best we can, the attribute accuracy, the aesthetic quality of things, and the hierarchy as we go from different scales, as we go from large scale to small scale and vice versa. So here we have a map that shows different resolutions of vector data, and so we have 1 to 10, 1 to 50, and 1 to 110. What we see here in the extreme southwest corner of Indiana is different levels of precision, different levels of spatial accuracy. And so we have what's the red one looks like it follows the line the best. The actual line, which we see here, is the base map. And the green's a little bit better than the blue, but the blue, it's awful. So not really awful, but the accuracy is just not good at all. I mean, look at it. It doesn't even come close to following the actual borders of Indiana. So if I'm wanting to study the watersheds in this particular area, using these particular maps, using this particular vector shapes, these shape files, these layers, would not be a good idea at all. But the objective here, this is just showing references. This is showing Indiana, its borders, and it's showing it at different resolutions, but it's more useful when we zoom out. You'll see that really these are indistinguishable from the Indiana border when we zoom out to, say, the national or world level, as I'll show here in a minute. Going across the state, we can see these same, just looking at New Albany and Louisville, this kind of border. It's finding it interesting how we have different ways to show our border. And so you might say, well, okay, where are we going with this? And so here, when we see that blue, that 1 to 110, you can see how it really doesn't follow the smoothness of the southern border of Indiana and Kentucky. In actuality, it's a river, and so it goes winding, zigzagging. So why would we want this? What would be the purpose of this? Well, when we're showing, let's say, when we're trying to map infant mortality rates across the world, including provinces and states, so you're looking at beyond the country level, looking at individual states and provinces and things and parishes inside of those broader categories, it might be useful to use this, because we're not really concerned about the precise border. Why would we do this? The main reason why we do this, and this is where I really want to emphasize here, is we're storing stuff on computers. And so anything that saves data, anything that saves just the amount of stuff that our computer has to do, the better. So what I had here is I looked at each of these individual shape files. I exported each of them. So I put them on my desktop, and then I inspected them using looking at the properties. The 1 to 10 meter was 31.1 millibytes. And so essentially what it is it's just a whole lot more dots on the red map, than the green, and a whole lot more than the blue. And so fewer dots means fewer stuff having to be stored somewhere. And so just in this example here, the files, how much smaller the file was. And this is one of the things you'll notice when working with ArcGIS. You might have heard me make this comment beforehand, or in the beginning of this particular semester, is it's been slow for 20 years. Anything we can do to make the computer go faster, the better, especially when working with GIS. And so here, essentially, I'm making a generalization about the Indiana borders because, let's say if I zoom out to this particular scale, at a much smaller scale than we've seen beforehand, now that little squiggly line of the Indiana southern border actually looks more like it should. The complex nature of it's really shown quite well, especially compared to the angular borders that dominate the rest of the state. And so for this particular scale, the particular resolution is ideal. We don't need to have this super high level detail the super big file, that is that 1 to 10 meter file there. We just need, in case here, the 1 to 110 to show whatever we're showing at this particular scale. So this is what I mean by where scale matters in terms of the level of detail and how it then influences the types of feature that we'll want to use in our maps. So here I went to Google Maps, and here if I zoom into Greenwood at this particular scale, you can see how it's made generalizations, and it's using a area to show Greenwood. And it's also then showing, as you can see here, most of the roads. I'm sure it doesn't have every single one, so it's kind of choosing to omit things. So it really doesn't need to show every single alley, every single driveway, every single cul-de-sac in this suburban area. And of course, we're making decisions about what types of icons to use for different types of features. What are the features that people are going to want to see if they're doing a search here? And so all this, people in Google, so it's probably a lot of algorithms and such, but essentially what they're doing is they want to produce maps in which if you just Google it and you just search for it, it's providing the stuff that they'll think that you'll want to know, stuff that they think you're looking for. So if someone's at this level of zoom, then that means, of course, it's better to depict Greenwood as a polygon. But if you're just kind of wanting to see where Greenwood is compared to the rest of the state, compared to the rest of the metropolitan area, of course, as you zoom out, Greenwood now becomes kind of, it's still an area, but you're going to see it becoming a point as we zoom out. And so as we zoom out, essentially Google, this is all algorithms, all kind of built in which they essentially have changed Greenwood from being a box, an area, a polygon, to a point as we change scales. Further, there's decisions made as far as what place names to keep on to the particular map. As we zoom out, we'll see fewer and fewer names, and so then it essentially becomes a deal where there's algorithms that decide which ones are the prominent cities to keep. And this is pretty much going to be the ones that are the largest, so it's based on population size, but then as you get farther out, it becomes just the cities that are around, other ones that are there, like Columbus, Bloomington, Terre Haute, and so on. Eventually, we zoom out far enough where Greenwood and Indianapolis have now become dots on the map instead of just polygons or areas. And so now we zoom out to this particular scale, decisions are made as far as, okay, well, what cities should I show? What are some other cities that are of use for this particular scale? So here I'm trying to show the Rust Belt or the decaying American industrial heartland. This might be a good scale to use because this is where all the manufacturing facilities are located. And so I'd want to show this, and of course the cities that are of prominence, the cities that would be important to whatever I'd be trying to show, would then want to be depicted on this particular map. In this case, Google just picks the ones that are the biggest, the cities with the biggest populations, and adds them to their map. With, of course, the roads, the major interstates, the biggest highways are the ones that are being shown here connecting each of these cities, whereas beforehand, we saw all kinds of roads. And so as we scale up, as we go to a smaller scale, decisions are made as far as which features to keep and which features to omit. In this case, every single highway would create confusion on this map. It'd just be a bunch of yellow blobs. And so that's why, as we zoom out, generalizations are made, and essentially features are removed. Just like here, where we have a particular watershed. This is the White Patoka watershed. And I'm wanting to show the streams and rivers of this particular watershed. Every single one makes it kind of, I don't know what I look. I see a lot of blue. It's just like a blue blob in this map. And so if I want to show the rivers of this particular watershed at this particular scale, it's probably just best to just show the important ones. That way I can kind of still see Indianapolis. I can still see where it goes, the park, and all of that. And so the highways, essentially here, it's clouded. And so there's too much stuff. And so I'm making generalizations about all this water features and just picking and choosing the ones that are best to show the waterways of this particular watershed. Now, if I zoom into Indianapolis, yeah, those individual streams are much more useful, and I can then keep those particular features because they're informing me. They're showing me the watersheds in this particular more zoomed in, smaller scale. So in this particular case, what I did was I essentially started teaching about the stuff, and now I'm going to then define the stuff I just explained. And so first off, simplification. This is going to be related to kind of the linear and aerial features where I'm changing the geometry. And so I'm essentially reducing the number of points, but I'm not trying to affect the geometry too much. I did that in that previous example of Indiana's borders. Essentially, I reduced, in some cases, the number of dots that made that border, that made up that line of the southern border as I zoomed out to a smaller scale. Smoothing, this is going to be something in which we kind of change the angular features. So we have maybe sharp angles, we're going to maybe make them smooth. So it's kind of similar to simplification, but the idea there is we're smoothing them. We're making it maybe instead of sharp angular lines into smooth curvy lines. Aggregation, we're going to do this a few different times, but we're going to also do this in an exercise in which what we're going to do is we're going to merge multiple features. Usually we think of them as points, merge them into groups, move them into polygons, and move them into areas, in which then, of course, we then take those points and we're making a generalization. We're finding a general trend. Amalgamation, this is where we're going to fuse two different areas or two different polygons together. This is also kind of referred to as merge. So essentially we take two different things, let's say Indiana and Kentucky, we merge them together and we call them Kentuckiana. So that's an amalgamation. Which is essentially the same thing as a merge, but merge is going to be, in this case, the definition is based on just linear features. Although today we think of them more kind of these terms, both being examples of merges. Collapsing, we've already showed that beforehand when I showed Greenwood as an area, Greenwood as a polygon, showing its true area, showing its true boundaries. And essentially what I do is that I zoomed out, went to a smaller scale. So Google replaced Greenwood with a dot. Or so a point. So that would be an example of collapsing. We also see airport runways, and so I have an airport runway, which have all the various runways, all the various taxiways, all of that. Instead, I just collapse it from all those individual lines or that polygon and just turn it into an airport icon. So I collapsed it into a symbol. Now, refinement's kind of complex. It's similar to collapse, but the idea here is you just kind of keep the features in a more simpler form. Maybe the example I used before of the watersheds would be a good example, and I got a visual here to show this as well from the book that might also explain refinement. Exaggeration is pretty self-explanatory here. The idea is we're trying to amplify a certain part of the object or feature just to really emphasize it so the map viewer says, aha, yeah, that's what I'm looking at. Displacement, it's actually, there's a mathematical procedure to it. It's not something which you just do just kind of haphazardly. But the idea there is we move features to avoid confusion. For example, in Indiana, we've got Interstate 70 that runs right next to US 40. And if I'm zoomed out at the state level, at the national level, but I still want to show both of those highways, both of those important interstates, to Indiana, I would separate them just a tad because they would pretty much be overlapping on top of each other. And so essentially I separate them, and that's what I mean by displacement. So essentially you separate features just so you can be able to see whatever you're trying to show. And so I'm trying to show these two interstates, I'm trying to show these two roads, these two very important east to west roads in Indiana, but I'm not zoomed into Greenfield. I'm zoomed out to Indiana, or let's say the United States. Then I'd want to displace them so that they're both distinguishable. They're both identifiable to the map viewer that, yep, these roads go right through the middle of Indiana, east to west. So here are all those particular operations. This is from the textbook. Then we see the original map in which we do that operation and create a more generalized map. And so we'll talk about each of these individually. All right, simplification is all about reducing redundancy. So that's essentially the idea here is we just want fewer dots. So we see on this particular map here, there's fewer dots. And so the general shape is still correct, but we got rid of a few dots that we don't need. And you see this in maps of trails at big state and national parks. Not every zig or zag or bend is shown on the big maps of the trails. And so just imagine we have 1 million points. If we reduced 20% of the points, that'd be 200,000 fewer points that were removed that did not really change the pattern on the generalized map. And so we're maintaining that spatial accuracy. We still see pretty much the correct shape, but we reduced the number of points, and as I showed beforehand, that means a smaller file. And this relates more into modern research in which GPSs are being used to involve space-time research. So we do this in our GIS class in which we create GPS data over time. And so if I have a medical study where I want to monitor both the time and location of a particular person's movements, I wouldn't want to record every single second. Although that'd be great, fine to have, fantastic to have that level of detail. It's just going to be a huge amount of data. It's just going to take up a lot of computer space, and I really don't need every single second. Particularly, let's say at night when they're sleeping, I don't need to see every single second where they're essentially at the same location. Even further, let's say they get up and go from their couch to the refrigerator. Is that really necessarily a change in their location? Is that really necessarily a change in their environment? No, not really. And so that's essentially redundant data that I don't need. Smoothing, as we see here, we take these sharp angular features and we make them more curvilinear. So, for example, rivers aren't like this too often. And so what we have is, in reality, rivers are much smoother. And so let's say I went out and I collected these points. I was out there in my waders. Is that what they were? Anyhow, I was out there in the river and I was collecting GPS points and I was going along. And so then I upload those points to my GIS and I said, well, I'll connect those points. And it created this particular line. I know in reality that, well, this particular river is curvy. So I want to smooth this particular feature. Aggregation, we have these points, and so essentially we want to group them in to polygons, and so points to polygons. So this is an example of aggregation. And so we have all kinds of aggregated data. So think of the United Census, all those individual points, all those individual surveys that were taken, that collects all that data. They then start grouping into areas, block groups, traffic analyst zones, census tracts, states, counties, and so on. Amalgamation, this is pretty self-explanatory in terms of this image here. We have some areas. These aren't points. These are area features, and we just lump them in together. So oftentimes you see this with lakes, which you might have a bunch of small lakes that are just grouped into an area called lakeland maybe. Or you maybe have individual land areas, so a bunch of islands that just say, okay, we'll just group them in together. So essentially we have these area features we group into other area features. So an example of this, we have, let's say, Indianapolis, Carmel, and Greenwood. So each of those are individual polygons. Each of those are individual areas. And so I take those areas, the Indianapolis borders, the Carmel borders, and the Greenwood borders, and say, okay, I want to create a group called Indy, Greenwood, Carmel. Just one whole grouping. Let's say for some reason I want to just collect data from those particular areas and lump them in as one particular feature. That would be an example of amalgamation. Collapse, take an area, instead show it as a point. So I showed that beforehand. As I zoomed out, Greenwood went from being a boundary to an area to a dot, to a point. And oftentimes at airports and other things, we change, we collapse it into a symbol. So it's essentially what we're doing is we're not really changing the geometry. We're not concerned that we're just changing the symbol. Here we have merging shown as line features. Essentially here, the idea is we're taking these line features and we're finding, and this is, once again, this is all done mathematically. There's a whole lot more procedure to this. It's not as simple as this, but the merging, the idea here is we're just showing a railroad line. We'll say, well, this isn't of concern to a railroad people, so we don't need to show every single line. We're just showing instead the general locations of the rail yard lines. So this is essentially merging. I'm kind of merging these features. And so we still have the general shape, the general pattern, but we have less features. Refinement, in this case, we have all the streams, and with this one, we just have the ones that we want, the major ones. So refinement, okay, I get it. It's kind of something in which we use other terms for, but there's a whole procedure to this process as well. So maybe I'm only wanting the ones that are of certain stream order classification. Exaggeration here would say I zoomed out, and when I zoomed out, it shows that there's really no inlet here. Would say zoom out, it's kind of lines almost look like they're together. I exaggerate, and so I zoom at the zoomed out image at the smaller scale. I still want to show this bay as far as having its inlet, and so I exaggerate. In reality, it's this, but I open it up just because I want the map viewer to know that there's an inlet here, that it's not a lake, because if these lines were together, of course, that would change this from being a bay to a lake. Here, two roads cross, and so you kind of have this emphasis to show where they cross and where one bridges over the other. And so just a way to enhance it, to make the viewer be able to see something more clearly. Oftentimes, like with, for example, West Virginia, a road might overlap with a railroad, which might overlap with a stream in those mountain valleys. So essentially, if I was wanting to show that, I'd want to maybe get them separated from each other, so it'd be easier for the map viewer. So they wouldn't be like red on top of blue, on top of brown, let's say, on top of these lines. They're just kind of on top of each other. I separate them, so I displace them. And then once again, there's a mathematical procedure to this. This also is an example of, let's say, the 70 and US 40 example I used beforehand, in which we have, let's say, one over here, the other, and so I separate them so that the map viewer can see them, can distinguish them from each other. And we'll end this video by focusing on simplification. It's one of those operations that we've talked about beforehand, but we're going to focus more on how this is mathematical, how there's a lot more to this than just essentially picking which points to keep and which ones not to keep. And so once again, the idea here is we want to maintain the integrity of a line or a polygon. We want its shape to be something which, okay, yep, it's true, it's good enough, but at the same time, we want to minimize the number of points. And so we're once again trying to find the critical points and try to keep those, but get rid of the unnecessary ones. And of course, there's a whole process to this. There's 5 different ones that the textbook mentions. The first one is called independent point routines. And it's just trying to keep the ones in which you put in a formula, say, I want to keep every 8th point, or I want to get rid of every 9th point. And so essentially what it does is it just goes through and does that. However, one of the problems is this doesn't really think about or take into account the neighbors around various points. And that's what we see here with the next 3, which is what's around us, what's around the neighborhood, what are the other points nearby to assess, okay, is this point significant? As we go back to this previous example here, these neighbors just looked over here, this particular generalization looked at these particular points and said, okay, these aren't really that significant, so we can go ahead and represent them as a straight line instead of a little bit of a zig and a zag. So then there's these 2 local processing techniques. And so once again, these both of them are a little bit different. We're really not going to get into them too much, but the whole idea is they're looking at the neighbors to assess whether or not to keep a point instead of just picking every 8th one or every 9th one. Finally, we're going to look at some global methods and 2 particular algorithms that are used. So the idea here is the processing, the routines, takes into account the entirety of the line, the entirety of the polygon, the entirety of a particular shapefile. So 2 of them that we're going to use, we're going to call them the Douglas-Peuchers, the DP, and then the Visverlingam, the V. So essentially, these are 2 different ways in which we take a particular shapefile. We take a particular area or polygon, and essentially what it does is it uses algorithms, uses intelligence to decide which points to keep and which ones not to keep. And of course, we'll look at our good friend Indiana. So what I did here is I took a 10-meter line, that previous one we used, and I put this into a website called MapShaper. And so what I said, okay, MapShaper, I want you to take this 10-meter shapefile, this relatively high resolution, and I want you just to keep 10% of the points. So essentially, I want you to remove 90% of the points. Huge savings as far as the data. Huge savings in terms of the amount of the file size when I eliminate 90% of the points. And so this red line here represents the DP, in which I said keep only 10%. And then I also did this for the Visverlingam. And so that one here is seen as green. And so once again, we go to the southwest corner of Indiana and see which one did better. All right, so which one did better? And so here we have the border, as we see here. And then I had the 10-meter line that I've used beforehand, which is relatively good. And then we have the red is the DP, which is pretty good. And then the green here. And so you can see kind of how they do things. And so you can see how, they've kept different points, but relatively similar. And so the red is essentially overlaps here with the green. See that there, and it's pretty much the same exit points as far as when the Ohio meets the Wabash down here in the southwest corner. So here's essentially what we've done is we took this particular line and we threw it into this MapShaper app and just essentially kicked out and reduced the number of dots. and thus made our file much smaller.